All right, guys, we are on the record now. In the last couple of lectures, we have focused on classification. Classification is a situation where X feature vector goes in, properties of some, for example, it's an animal. You have the weight, the size, where the horns are present or not, and things like that. What you have to determine is a class. Which class of animals does it belong to from a category of animals? Cow, duck, horse, we took that as an example. So here, cow and duck and horse, they're considered classes. And associated with them, are certain set of attributes, more or less, that gives you a notion or a concept that this is a horse, this is a cow, and so forth. Now, the set of all these classes must be finite, and it's called the category. Now, we talk about machine learning algorithms as we were talking about them. We have the discriminant analysis. In the discriminant analysis, we make the assumption that each of the classes, they occupy fairly separated, or they're fairly clustered. All the instances of a class are fairly clustered in the feature space, and they are not just clustered, they're clustered in the shape of sort of a bell hill. And so the ducts will form here. We have volume versus weight, and the ducts are centered in one part of the feature space. Cows are big and heavy. They're centered at another part of the feature space. And so what do? You go to the bell hills, at the tippy tops, hilltops. You connect them, and then you take a bisector. You get a pretty good decision boundary from that. So that brings up the concept of a decision boundary. So what were the assumptions of discriminant analysis? Each class instance are clustered around a different center in the feature space. These clusters are approximately bell hills, or more formally, have a normal or Gaussian distribution. And linear, we can do linear discriminant analysis if we can say, the bell hills look more or less alike. They just happen to be at different places in the feature space. Alike in what sense? In terms of their variance, how much variance they have in one dimension, and two dimensions called the covariance matrix. But okay, let's stay with the word variance for now. Good thing about discriminant analysis is, but suppose your bell hills look quite different, then all is not lost. You just have to account for two different variances, and or in higher dimension covariance matrices. Then the analysis gets a bit more complex. Your decision boundary is not straight; it becomes a quadratic curve or quadratic surface, and still it's very doable. In the modern world with modern computing hardware, it works very fast. So in general, these are straightforward algorithms to do that. Right? One advantage of discriminant analysis is it naturally does multi-class classification. So for example, if you have three classes of animals, cows, ducks, horse now, that is perfectly okay. You can connect the hilltops, take the bisectors, they'll meet. And so you can still partition now the feature space into three regions. One for ducks, one for cows, and one for horses. So it's a very natural generalization to a multi-class classification. Then we talked about the fact that sometimes those hills are overlapping. When the hills are overlapping, then you take the bisector of the hilltops. But now what happens is you will have errors. Horses, you will have a pretty good region in which it's hard to tell whether it's a cow or a horse, for example, right? Their weight with respect to weight and so forth. So then you will have error rates that will come. Error rates you always have in machine learning, right? So how do you quantify error rates? When we talked about error rates, we generalize. We say that whenever you do classify, irrespective of what classifier it is, we build something called a confusion matrix. In a confusion matrix, suppose you have the cow and the horse. How often could we identify cow as cow? And how often we confused a cow to be a horse? And likewise for a horse, how often we got a horse as a horse and we confused horse as a cow? Sort of that. So in this, the most basic measure is accuracy. How often we got it right. Error rate is how often we got it wrong. Now, just that in itself is not enough because sometimes the data is the classes are very imbalanced. For example, if you're testing for people for some rare diseases, most of the tests will come out negative. People are healthy, and only a few people will be sick. So the thing is, you can have very high accuracy, but it may not mean anything because there's a huge imbalance in the classes. So then we have to think what are other measures that we can use to quantify the goodness of our models. Now we look at
Asif,
yes.
I'm sorry to interrupt. I just have one question, which we have used this COVID-19 example.
Mhm.
I just have one query regarding the naming convention. So we have said that a positive patient who really has COVID-19 will be a true
Yes.
positive, but then
Yes.
who is healthy but still has been labeled as a positive person, we have called it as false negative, right?
No, 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 sorry. No, that was a mistake. That's
Yeah,
a very good point that you discovered. This is not a false negative.
it's a
Uh,
false positive,
false
right?
positive. Yeah, this is a false positive. And uh, this is a false, a healthy person having a discovery is
False, true positive, true negative.
healthy. Healthy, no, no, hang on.
False negative.
No, 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 false negative. This was right, actually. Yes, I apologize. See, when a positive person you mess, it's a false negative. So it was correct. And this is false positive. Means you marked a positive case as negative. That negative is false. When a
But then,
person who has COVID, this look at this 50 people, they have COVID, and you say, no, I mark them as healthy. So what did you do? You forgot to catch them, isn't it?
yeah,
You had
yeah.
a false negative. And then you, in the opposite case, when they're healthy, but you call them to have COVID, then you are having a false positive.
Okay. Yeah.
So yeah, this naming is correct. So that's that. And we talked about the fact that this sort of analysis, discrimination.
Can you repeat it again for false negative and false positive?
See, a false negative is when you missed a positive case, when your classifier misses a positive case, right? So, for example, you have COVID, but the test comes out negative. So that negative is false, right? It is not correct. That is a false negative. Are we clear about false negative now? So in this confusion matrix, 50 is the false negative, right? Anil, is that clear?
Yes.
And then with healthy people, if you mark some healthy people as having COVID, you mark them positive for the disease. That is wrong. That is false. If it helps you, put the word wrong instead of false. In colloquial language, you'd say wrongly identified as negative and wrongly identified as positive. Right? Let me put the colloquial meaning here. Well, I don't want to put it. Yeah, let me put it somewhere. Let me create a space here. Actually, um, this is true, negative. Yeah. So false positive, you can think of it as wrongly identified as positive, right? And false negative, wrongly, wrongly missed or did not missed some wrongly missed some positive cases. So,
So the positive and the negative here denotes having disease or not having disease.
yeah, positive. You have to decide on the convention. That is why I said COVID.
Okay.
We define that as positive because hopefully it is a less likely situation. It is a signal you're looking for, missing some positive cases. That's how it is. in general, this is true. For example, the doctors, when they, physicians, when they look at your medical report, lab report, um, if you are healthy, they'll say nothing is remarkable. There's nothing remarkable observed. Believe it or not, that is very good news, because if a physician looks at a lab report and says, oh, there is something worth remarking or there's something positive, that is when you need to start getting worried, really worried about it. So positive usually means, in medical literature, usually it means an adverse case, COVID, like having COVID and so forth.
So for I say for false negative, did you mean like wrongly missed some positive or wrongly missed some negative?
Yeah, no, false negative means you missed, like you missed some people who are sick and you send them home. So which is disastrous, they can die at home. So false negative is pretty disastrous. False negative is pretty disastrous. You wrongly missed some positive cases in COVID, for example. See, you just think about this way, read it backwards. A thing is marked as positive, but it shouldn't be. So what does that mean? If positive is sick, a person is marked as sick, but shouldn't be. It means he was a healthy and you just marked him as sick. All right, there will be some adverse impact. Now think about the other one. Negative of being sick is healthy. False healthy. The person is not healthy, but you marked him as healthy. What does that mean? That is a scarier situation. You missed out a patient, isn't it? And that is a good point. Actually, we'll talk right about that in a moment. So we talked about accuracy and so forth. Then we talked about logistic regression. What is logistic regression? And I said that we went through the derivation of the logistic regression. What it means in simple terms to review is the further you are from the decision boundary, the more clear the signal is. You're very sure that it is a blueberry if you are far from the decision boundary in the lower region. And if you are far away in the positive region, red region, from the decision boundary, are much more sure. So distance from the decision boundary is called the distance function. We will leave it as that. Now the question is, how do you relate it to the probability of its being red, for example? So we went through a small derivation which says that, see, probability goes from 0 to 1. This distance is going from minus infinity to plus infinity. So how do we map one to the other? And it turns out that from probability, we can get odds. When you get odds, it goes from 0 to infinity. Now then, if you therefore exponentiate the distance, e to the d, exponentiation always takes you from 0 to infinity. And you have essentially solved the problem. You have discovered a way that you can deal with it. And in fact, that is the derivation of the logistic equation. And this equation is in all the literature, it will be presented like this in your textbook. If you have been reading your textbook, you'll see a thing like this, right? This is in fact the way it is mentioned in your textbook. It is an example of something called a sigmoid function. Sigmoid functions are S-shaped curves. They are stretched out S-shaped curves, and their qualities are they're continuous. Of course, they're continuous function. It is smooth, means it doesn't have rough sudden changes of value. Smoothly the values rise, monotonically increasing. You see the gradual increasing. It doesn't start changing direction and moving down and then back up again. Continuously increases. And it has two asymptotes, the lower asymptote, which is at 0, and the upper asymptote, which is at 1. What it means in a sense is, once you are sufficiently far from the decision boundary, you pretty much know what it is. It's a blueberry or a red berry. So these type of functions they belong to a class of functions called sigmoid functions. But they are all over there in nature and electronics and so forth. So I won't go into that. So today, what I would like to do is go back to this confusion matrix. I can see we are having a little bit of a difficulty coming to terms with it. Let's go back to confusion matrix.
Asif,
Yes.
I'm sorry. Can you please announce for ML200? We were supposed to announce that.
Okay, sure. Let us do that. Guys, I'm taking in registrations for ML200, the continuation of this workshop. If you are going to register for it, please drop a word to Prachi right now. Do that. I'm trying to estimate how many people are interested in taking it. Then I'll open it to a wider audience. It helps us plan a little bit. So please do drop a word to Prachi right away.
As if a quick clarification, would you mind clarifying the odds, probability, and likelihood?
Okay.
Okay.
All right, let's do that. Let's keep it as it. After confusion matrix, I'll also talk about odds, probability, and likelihood. These are three different words, even though in popular language they are considered the same. We will talk about that. Let's keep it as something to do in the latter part of the class. So let's talk about the confusion matrix now. Let's go back to the example. See, suppose this thing is true, false, huh? And you mark it, you predict it as true. Okay, let me move it in a big box here. Something is true, something is false, right? And then you predict it as true, or you predict it as false. And by the way, you can write this matrix, transpose this matrix. You can put the true values at the top and the predicted values here. Up to you how you do that, right? I'm doing it like this, and you can do it another way. So this is, we'll give a name. Let me just call it A, B, C, D. So what is A? Is it true positive? Suppose in this situation, is it true positive? So just to put a meaning to this, right? Let me put something. We are testing for COVID, let us say COVID-19. So A is a person has the disease and you classify as having the disease. Is that a good thing or a bad thing for a test? Come again?
Good thing. It's a good thing.
It's a good thing, and you would call it a true. It's a true positive. Then B would be what? There was a person sick, and you detected it as not having the disease. So this would be what? It is a false
Positive.
negative.
False negative.
Negative. Because you mark this guy as healthy, but the person is actually sick.
Okay.
What about C? C is the person is actually not sick, but you declare that the person is sick. So this is false,
False positive.
right? This is false positive, and D is true
Positive.
negative.
True negative.
So with that in place, people have created quite a few measures. So let me take the total. Total is equal to A plus B plus C plus D, which is the total number of instances. Accuracy is defined as A plus D, the principal diagonal, A plus D, not B, A plus D, the ones that we got it right over total. Error is equal to B plus C, the off diagonals, those are the mistakes over N. So far, so good, guys. I hope accuracy is what proportion you got right. Error is, of course, what proportion you got wrong, right? So accuracy is 1 minus errors. Error rate. Accuracy. Would you agree? You can just add up these two things and see this is true. Now, it turns out that we have in the industry, this word classification is used in many, many fields, and a whole lot of different terminologies have come about in this space. And let me walk you through the words that people often use in this space. In modern literature, we speak a lot about two more things called precision and recall. Are we together? So what is precision and what is recall? Precision is how precisely, the true positive over the positive test cases, true positive over positive test cases. So, by the way, guys, may I suggest that if you do have your textbook, go over to page 148 and 149, and you will see that these things are explained there. All right, guys.
Yeah.
So these things are explained out there. Then the recall, and so all you have to do is recall. And recall is equal to, actually, no, this was the recall. This is, I should put it in the different columns. True positive over positive. Positive is recall. And the precision is slightly different. But okay, let's stick to recall and then we'll come to the precision stuff in a moment. In the case of COVID, do you want a good recall or a good, what do you want? Is a good recall a good thing?
No.
What do you want to do? You want to have a test which is very good at uh, not messing people, right? People who are sick, you don't want to mess them. Isn't that true?
So recalling
So
means we have
yes.
missed it, right?
Come again?
Recalling means we have missed them. That's why we are recalling again the test to retest it again.
No.
So is it like, do we want to capture everyone, like all possibility, like throwing a wider net?
No, it is simple. See, it is just made out of this matrix. In this matrix, a true positive over positive. So true positive is this. Total positive is A and B together make it total positive. So in other words, a high recall means if you are positive, you're marked as true positive. Your classifier finds you as positive, right? So what it means is that you don't have false negatives. Now, for medical situations like this, you want a very high recall, isn't it? You don't want to have false negatives because false negatives can be fairly disastrous. Does that make sense, guys? See, the definition of recall is true positive over positive. So it is A over A plus B in this picture. Am I making sense, guys?
So recall is good, Asif, or it's bad?
Good recall is very good. The better the recall, the less you have false negatives, isn't it?
So Asif, so let's like take the cancer case. So we want to capture everyone who has a cancer.
Right.
In the process, we are also capturing like people who don't have cancer. So that means we are trying to capture as many people as possible. So that is the recall.
No, it is not. So suppose you have, let's say that you have a population, and in the population, 16 people have cancer, right?
Yeah.
A good recall means, so now let us say that your classifier caught only 3. So
Yeah.
your recall would be 3 over 16. Right? Whereas what do you want? A good recall would be all 16 out of 16, isn't it?
Yes.
That is the point. That is what recall is. Right? That is why recall is also called the sensitivity of the classifier. How sensitive it is. Can it just detect it? Like, for example, we say that the PCR is a very sensitive test. This uh, RT-PCR for COVID, the reverse transcription PCR, is very accurate, very sensitive. Why? Because it does not miss people. That is why it is the gold standard. its recall is near perfect, close to 1. Are we together? Right. And precision is one, you take the false discovery proportion. So 1 minus this. Let us take this. What is a false positive rate? B. What is B? This is a false positive rate, isn't it? So 1 minus false positive rate is precision. So precision, and this is very subtle actually, guys. In the beginning, you will keep getting a little bit lost. Now think about it. If you have a false positive, like if you have actually, sorry, a false positive is here. This is it, C. So it is 1 minus C over N, right? What it means is, how often do you, precise means you don't get a lot of false positive, false positives. Good recall means you don't get a lot of false negatives, isn't it? So suppose 16 people have cancer, you don't want to miss out on them. You want all 16 to be caught, or 15 to be caught at least. So that is a good recall. Good precision is a slightly different. It says how not to be trigger happy. A trigger happy situation would be that you mark everybody as positive, right? Suppose one test, if you think about it, if I cook up a test and whosoever comes to me, I have only one answer to that. You have COVID, right? So what is my false positive rate? It will be practically everybody, like everybody minus the true positive, right? I'm marking everybody as sick. Is that a good test? It is not a good test because it's not precise. It is not able to distinguish between people who have and don't have it. So precision means you have a low false negative rate. So what is, are we getting, guys? If you have to look at ABCD, what is your false negative rate? Or false positive rate? What is your false positive rate? Yeah, which one is it? In terms of A, B, C, D, what is your false positive rate?
C.
Yeah, it is C. This is false positive. So false positive is C over N, the total, right? So C is the false positives and divided by the total is the false positive rate. Am I making sense, guys? C over N, let me just put it this way, false positive rate. Let's just focus on this, C over N. Does this make sense? Right? Can we just reason through that? If we have total N data points and we have C people, we mark them as false positive, which means that let us take a population again of 1,000, 16 people are sick, right? Have cancer or something, let us say. But we have, our equipment has marked 100 people as sick. Would you consider that to be a good test? It is not a very good test. You say that it lacks precision. It's not a precise test. A precise test would have very low false positive rate. It won't miss, it won't be trigger happy. Think of it that a precise tool is not trigger happy. It doesn't just quickly mark things as positive.
So you're looking for a precision close to 1 or 100%.
Yes. Both precision. Now, ideally, what you want is you want a precision close to 1, high precision and high recall. Unfortunately, it is hard to achieve. What happens is that in the beginning, as you use better and better algorithms, you improve your model, both your precision and recall will improve. But after a little while, it becomes a trade-off. And I'll explain why it is a trade-off. See, if you if you become very trigger happy, if you are willing to lose precision, recall is easy to take care of, isn't it? For example, you mark a lot of people as positive for the disease. Well, the hope is that all the people who really have the disease will also get captured, isn't it? On the other hand, okay, let me make it draw it in terms of a picture here. Let us say that you do. Let me just take it as one dimension. In this, all this, all the points in this value, some x value, and I'll just deliberately take it as one dimensional. So let us say that there is some degree of, so do you notice that between the blue and the green, there is some degree of overlap? Let us say that this is positive, true positive. Blue is positive and green is negative cases. So what is one way not to, let us look at it. What is one easy way not to miss any of the positive cases? If I put my decision boundary here, let me call this decision boundary D1. Do you notice that I capture all the positive cases in this picture, right? So positive cases caught. On the other hand, the demerit of this is lot of false positives. Do you see that, guys? Why false positives? Because a lot of these green points I have marked as blue points. Isn't it? This is, and this, if this is the decision boundary. Can you see that, guys, that this is the area of mistakes? In this particular situation, one-dimensional problem, this is the area of mistakes. And if I put the decision boundary at D1, I'll get a lot of positive cases, right? All of them will be caught, but I will have a high false positive also. On the other hand, if I make my decision boundary here, D2, what happens for D2? For D2, D1, D2, what happens here? Do you notice that all negative cases are caught, right? Cases are correctly classified, but lot of positive cases are missed. Positives is this obvious? Are you guys understanding this? Just look at this example. That you have a trade-off. Which one would you choose? In the extreme D1, you get all the positive cases. In D2, you get all the negative cases. Each of them have a demerit, isn't it? In the case of D1, you have a lot of false positives, and in the case of lot of, so i.e., lot of false negatives.
So, sir, your false negative rate shouldn't be over n. It should be over a plus c.
Come again?
Sir, in the formula above, false negative rate, because you said c over n, shouldn't it be c over a plus c?
Oh, yes, absolutely. You're right. I shouldn't say. That's a very good catch. The false, there should be a plus c. You're right. A plus c, and yeah, that's a good one. Thank you. A plus c. Right. So, guys, look here. But intuitively, when you look at the decision boundary D1 and D2, which one has high recall? What is high recall? High recall is there when you don't miss a positive case. Which between D1 and D2, which one has higher recall?
D1.
D1 will have high recall. And what about D2? It has
High precision.
high precision. Right? Why is D2 high precision? Because it tends not to give false positives for you. Right? So you have a pretty the false positive rate is 0. So you have high precision. So what happens is that you have to decide in a situation where data is, there will always be a region in which it is ambiguous to different degrees. And so you have to decide ultimately where will you put your decision boundary, right? Wherever you put, as you slide your decision boundary between D1 and D2, right? So think about this. This is there. Your D1 is here. D1 is here. D2 is here. In this interval, you are putting your decision boundary either here or, sorry, either here or here. No, this was not very useful. Here or here or here or here. And wherever you pick, you're doing a trade-off between precision and recall, isn't it? And so that is the catch. In the beginning, when you are still training the model or trying new algorithms, usually both precision and recall will go up, accuracy will go up, and so forth. But after a little while, where you put your decision boundary exactly, you will be doing a trade-off between precision and recall. If you go more for precision, you lose recall. If you go more for recall, you'll start losing precision. And so you have to be careful. And so let me, it is usually explained using a particular curve. It is this. This, let us say, is false positive rate. And this is true positive rate. Right? So now, look at this. What happens is your true positive rates means how much of the true things you caught. And what happens in the beginning? When that false positive rate is 0, when can you have a 0 false positive rate? Suppose, yeah, imagine that your decision boundary is at this point, D3. So what will happen here? And D4. Let us look at these two extremes, D4. In D4, D4 is way beyond. You mark everything as negative. Do you think you can have a false positive rate? No. Everything you're marking as negative, isn't it? But at D4, there are no positive samples left behind either. So in this, so if you plot it out, you will end up with a curve. And let me just draw the famous curve like this. What happens is, if you are too strict in calling something positive, right? You say that you need to be 100% sure, then only you'll mark it as positive. Well, what will happen is, one easy way to be sure of is mark everything as negative. If you mark everything as negative, you won't have a false positive, but you won't even have a true positive because it's a useless system. You don't have a true positive. Are we together, guys? Right. On the other hand, if you want to maximize your true positive, let me just say percentage. This is 1 and 1. One easy way to maximize true positive, you mark everything as positive. So you go with the decision boundary D3. You say everything is positive. Well, then what will happen? Your false positive, in other words, a lot of negatives, these green things will get marked as positive, isn't it? When these green things get marked as positive, then you have a false positive rate. Right? And so this is true positive, false positive. There is a trade-off between the two. And this particular curve is quite interesting. It is called the ROC curve. And I'll explain what ROC stands for. Whenever you have a classifier, it turns out that while this is a fact of life, you can compare one classifier against another. So if you think of this rectangle, let me look at this rectangle, this entire rectangle, this rectangle is a square. Actually, it's a square of area. What is the area of this square, guys?
One.
Base is 1 and height is 1.
One.
It's 1.
It's 1, isn't it? So now what happens is, suppose in your classifier, you are still doing a trade-off between false positive and true positive, right? But nonetheless, and you get this particular curve. If you compare it with this curve, which is the 45-degree angle, diagonal, right? The gap between these two is a measure of goodness of your model. Measure of goodness of your classifier, one of the measures. Let me explain this. So suppose you were just randomly guessing. If you're randomly guessing, your then what will happen is you can in a system that just randomly guesses. One thing is it can always guess everything is false. Everything is negative, right? So then the false positive rate will be 0. No. True positive rate will also be 0. On the other hand, suppose you're just tossing a coin or picking up a number between 0 and 1. Suppose 10% of the cases you mark as positive. Well, your true positives will go up because now some positives are being marked as positive, but your false positive will also go up because quite often you have just randomly picked something as positive and it is not positive. So a bad classifier, its curve, ROC curve, will look like the diagonal line. A good classifier can be even better. The perfect classifier would be something like this. Right? A very good classifier. Classifier. A very good classifier means for a very, very low false positive rate, you're capturing all the true positive cases. Right? So what will it mean? This is a perfect thing, right? You have a very high true positive rate and a very low false positive rate. Means it has very high precision and it also has very high recall, isn't it? That is the gold standard. Can you create a classifier that has that has goodness on both sides? Now, usually what happens is, practically in real life, your classifier's ROC curve will be somewhere between the diagonal, which is the useless, to between the diagonal and the red. The red ROC curve. So this is what you will get. Like, look at this white line. The white line here is a much more realistic example of what you will see. Sometimes you get very good classifiers. It becomes to get closer and closer to the red situation. So the way you measure the goodness of your classifier, one way, is that you look at the area under the curve. This area. Now, this area under the curve, you realize that it will be somewhere between half and 1. Half, why? A bad classifier is this triangle. Triangle's area is half. Yeah. So this is there's a term for this. It is called the AU ROC curve. It's a very important term. You'll find literatures ROC. Typically, and let me just emphasize the capitalizations, etc. ROC. It stands for area under the ROC. Right? So this will go between half and 1 usually. Yeah. Well, actually, theoretically, it can be between 0 and 1. Well, between 0 and 1, but usually, why 0 and 1? You can actually be worse than random guesses also. your curve can be below the diagonal, usually between half and 1 for a reasonable classifier. And this is quite important, guys, this area under ROC. Now, what is this word ROC? I didn't quite explain. ROC stands for receiver operator characteristic curve. Characteristic curve. Now, what this is a very weird sounding word. Like, who would have guessed something, a term like this? Where does it come from? It comes from, actually, it has an interesting history. It didn't come from the machine learning literature, actually. It came from signal processing literature. So let me set the context for that. The context for it is like this. Imagine that you have a channel and you are sending a signal from here. The signals that people send in digital age is 0 or 1, right? And now here you're receiving 0 or 1. Now what happens is that when you send a signal, electrical signal, 0 is 0 voltage, 1 is some voltage. Let us say it used to be 1.1 volt, 1.5 volt, 0.7 volt. I don't know what it is these days. Whatever voltage is, high voltage, low voltage. Now what happens is, as the signal propagates, when you measure the voltage here, it is never quite 0. It may be, let's say, 0.3. And now what do you interpret 0.3 as? Or it may be 0.2, or it may be 0.6 or 0.7. The values that come out, now what you have to do, the numbers you are getting are not so clean, but you need to determine whether it's a 0 or 1, because you know that the sender is sending 0, 1 signals. So a bad channel or useless channel is, you keep sending 0 ones, but what you discover here is completely random. Right? So this channel acts like a classifier. Input went as 0, 1. What did you detect it as? Because now these are your features. Based on these features, you have to determine whether it was a 0 or a 1. Right? So that is why it was the receiver operator, the receiving end operator. So what they did is they realized early on that this consideration happens. You know, if you think about it this way, if your voltage for 1, for positive is, let's say the voltage goes from 0 to 1.5 volts. And suppose you insist that you must get 1.5 volts, otherwise you won't accept it. You won't accept it as 1, you'll mark it as 0. So what will happen? All your values will be 0, because 1.5 volts will almost never cleanly go to the other end as 1.5 volts. They may be less. So your false positive rate is 0, but your true positive rate is also 0, because everything is 0, low voltage. On the other hand, if you set the voltage to some value, but your channel is completely useless, then you will essentially you will have this curve. The diagonal curve is what will happen. False positive will increase, true positives will also increase. At the end of it, suppose you set your cutoff voltage as very low, 0.01, even a little bit of a voltage, and you mark it as positive. In that case, your false positive rate will become very high. And it so happens that your true positive rate will be high, because all the things are practically being marked as high voltage or 1. So that is the history of this curve, receiver operator characteristic curve. And again, in hindsight, you look at that, and what they were doing is essentially doing a classification on the channel, signal received at the other end of the channel, right? And so the word has stuck from there. We use the word AUROC. It's a pretty mouthful. Area under the receiver operator characteristic curve. It is one of the very good indicators of how strong a model, how effective a model that you have built for classification. Are we together, guys? Is this concept clear? Because at this moment, it will take you a while to absorb false positive, true positive, and so forth.
Asif, on this graph, I have a question on the red one, which is the good classifier. So, but even on the good classifier, when the false positive rate increases, the true positive should why is it flattening at around 1 is my question. I'm not able to figure that out.
Yes, yes. So imagine that, see, in a red classifier, what do you want to do? You want to put your threshold somewhere close to this, because at this little value of the threshold, this point, your false positive rate is very low, but true positive rate has already reached a saturation point. See, the maximum value true positive can have is 100%, isn't it? 1.
Yes.
So it has to saturate at 1. But the question is, how much did you sacrifice? While it jumped to 1, how much did the false positive rate jump? So for example, in this case, let's look at this point. To achieve this level of true positive, you sacrifice quite a lot. You're having a pretty high false positive rate also. So this white line is not as good a classifier as the red one, because in the red one, you don't need to pick these points. You reach a point of good saturation right here itself, isn't it? Where you have a very low false positive rate and already you have achieved as much true positive rate as you want. Near saturation level true positive rate, which is why you say that good classifier. Is this becoming clear now?
After it reaches 1, should it just because it has to stay at 1 even though the false, but why would the false positive rate increase after that? That's because it has already reached 1, right? The true positive rate has reached 1 with that point. So how would the false positive rate increase? Why would you draw the graph further is what I'm asking.
The reason you do that is that when you have a true positive is high, but if you put your decision boundary in the wrong place, right? If you like put it too much, like let's think in terms of voltages. If you put your voltage at, let's say the voltage goes from 0 to 1.5. Suppose you put your voltage as 0.1. Anything above 0.1 is positive. So what will happen to your true positive rate at that cutoff? Very high true positive rate, because everything is being marked as positive, isn't it? But you will also have a high false negative rate. False positive rate. True positive rate will be high, false positive rate will be high. Now let's take the other extreme. Suppose you take it at 0.5, right? And let us say that the signal is coming out very clean, or 0.75, right? Half of 1.5. Let us say that the signal is truly coming out very clean, which means that the low voltages, like when you're transmitting a 0 or a low voltage, the values that you get are something like 0.1, 0.2, 0.3, something like that. And when you're transmitting a high voltage, you're getting something like 1.3, 1.4, 1.5. There, what happens? If you put your cutoff at 0.75 volts, you will see that you get a pretty good true positive rate. Right? You capture all the positive cases and you don't have false positives. In other words, low voltages are not being confused as high voltages, isn't it?
Okay. Yeah.
That is it. So that would be in that channel, that would be a good value to pick. Yeah? Not 0.1, but 0.75 would be a good value to pick. Right? So this curve helps you determine that, because see, 0.1 takes you to this point. You have a very high true positive rate, but you have introduced a lot of false positives. A lot of low voltages are being detected as one, as high voltages. So that is why once it saturates, going any further in this direction is a disaster. You don't gain anything. You begin to lose it. In the red line, once you have saturated, you don't want to go put your threshold in such a way that your false positive rate increases. You want to just stop there, right? But in a situation like this, look at the white line now. In white line, you don't have a choice. Suppose somebody says I want this. It's very hard to pick a particular point and say this is good. You will have to determine how much of false positive rate you can tolerate. And if you tolerate, let's say that you can tolerate only a 20% false positive, right? Then your precision goes down, but your recall, true positive over positive cases, also goes down because you are missing out on on positive cases, right? So
Okay.
that is the trade-off between precision and recall.
Okay. And just one follow-up question. So will the true positive and false positive, what we are doing depends on what we measure. For example, in this case, we took the detecting COVID, right? In this case, you said it is good to have um, um false positives than the
Yeah,
true
false
negative, right? Depending, but say for example, we are measuring the earthquakes. Then it's little bit different how you think about it. It's even
absolutely,
good.
absolutely. It's a
How
very
will
good
that
point.
vary?
Yeah, I'll give you as an illustration. See, when you're talking about serious illnesses, you want a good recall. You want a situation in which you don't miss positive cases, right? So your false negatives are low. You don't have false negatives. You catch all of them. 16 people have cancer. A good cancer test will go and catch all 16 of them, right? On the end, let us say that instead of 16, it found 18 cases. Then two people, it will be a nuisance. They will be called having cancer. They will go through further tests. And then the doctor will come with the pleasant news that actually it was a false alarm. You're totally fine. Right? So the person will just go through a couple of weeks of stress. On the other hand, you don't want to miss a guy who genuinely has cancer. So in medical situations, you focus on not having a false negative. You just want recall to be high. But let us say that you are lending money, right? And you're, you're you want to determine that uh, is this guy good enough to loan money to, right? In such a sense that he will keep making payments to you. There, you have to be careful. You don't want to be absolutely sure, right? Or rather, you do probably want to. When you lend money to others, you do want to be pretty sure. Uh, which way will you guess? Suppose you have 50-50 chance that this guy may or may not return you the money. Will you give him the money? You probably won't. A bank won't give him the money, right? The bank need a very high degree of assurance that the money is going to come back, right? With interest, of course. Then they will give you the money. So the where you put cutoff and how you look at it is different.
So there we are not focusing on the recall. Is it that's the good? That's the other one.
Right. What do you want to do there? You want to go with high precision. You want to
Precision.
capture all the guys who uh, who will return you the money. You want to capture all of them. And occasionally there may be a bad apple, but the point is you make so much money uh, from the good guys that one or two bad apples don't matter. No, it's the cost of business.
Sir, can I add something?
Sure.
Yeah, very nice. Nicely you are explaining. But I think, in other words, a true positive rate, I can label it as a sensitivity, and false positive rate, I can label it as 1 minus specificity. So if we label like that,
Yes. Yes.
yeah, if we label like that, one test cannot be 100% sensitive and cannot be 100% specific. So that's why we have in medical one test we particularly call screening test, which has a very, very high level of sensitivity. And then we do secondary test, which is confirmatory test. So that test has a very high specificity level. So rather
Yes.
than having one test with, we cannot have one test with high specificity and high sensitivity. So we
Yeah.
have like two different tests.
Yeah. So Sukhpal, being a doctor, he introduced two words: sensitivity and specificity. Let me explain what it is. Sensitivity is the same as recall. It is another word for recall. Specificity is actually not precision. It is a new measure. It's one more metric. It is it is the false positive over negative. Right.
Asif,
And yeah,
I'm sorry.
just
So can
one
we say
minus
in simple terms, like sensitivity will be the initial screening and specificity means like it's actually there?
right. See, sensitivity is See, when you do early tests, you want, yes, you want high sensitivity. But after a few tests, you want high specificity. That is what Sukhpal is trying to tell. In the early test, even the slightest doubt that this guy may have cancer, you want to mark him as positive. You want to send him for further testing, right? And it happens, for men, the prostate, as you go across 40, you will realize that it happens. They'll do some blood test, etc., etc. Sometimes the blood test comes out positive. Then on further probing, it turns out not to be a problem or something like that. Women have it, these scary moments even more often, They go for something called a mammogram, and then even the slightest fogginess or anything, and the doctor will say, oh, we need to do further test. So there, you want to have high recall. You don't want to miss out on any case. But then you don't want to continue doing that, because the next test and the next test and the next test, the subsequent test should be gradually focusing on the specificity. Because now in that pool, there is already a very high positive rate. A lot of people are likely to be positive. You just want to weed out the negatives. So you want to be very specific. If you don't have it, don't say yes. No, don't unnecessarily put somebody on a chemotherapy. So, and that is a very good way of saying that where is one thing, where should you emphasize one versus the other? In the early test for a disease, you want to go with sensitivity or recall. In the later test, when you want to be absolutely sure, and you have already gone through a barrage of early tests, you want to be very specific. Does he genuinely have cancer or not? Does she genuinely have cancer or not? You need to have specificity. Right. So
Specificity is true positive by n, could be that, right?
what is that?
Here you said 1 minus specificity is false positive by n.
Yeah, that is the definition of it. So you can write it as, or another way to do that is you can say, therefore, specificity is take all the cases and subtract the false positive and look at the value. Right? So think about it. In the later test, you don't want to have false positives, isn't it? Suppose you are one big oncologist specialist, and some doctors have sent patients, and they say that in 5 different medical tests, they have turned out to be suspicious. They may have cancer. What do you want to do? N number of people are there. You want to remove the false positives, right? Because you already know that false negatives are not there, right? Because the early test took care of the false negatives, isn't it? The person who did the mammogram was trigger happy. Even the slightest cloudiness anywhere in the X-ray, and he would say, oh, maybe you have cancer, right? Go and get further test done. So you're not fearing that you will have a lot of false negatives. But at this moment, you want to just remove the people who don't have cancer at this moment. So specificity is therefore this ratio. And a good test would just have a very small false positive rate. In other words, it is still true. Occasionally, you might you might end up sending a perfectly healthy guy through chemo. Does it happen? Well, at least I know that in India a few years ago, when I used to be there, it used to happen. I don't know whether it still happens in US or not. Sukhpal, does it still happen? A false positive, like you put a healthy person through chemo?
Sir, so nowadays you are giving very nice examples, but a very good example here we can add is AIDS, HIV, ELISA. So we do screening test, ELISA, and then we do Western blot confirmatory test. For example, you were saying breast cancer, right? So we quickly do mammogram. So that is just taking X-ray of the chest. And if there is anything wrong, mass or any calcification, so we don't know. Maybe that's most of the time that's benign. But then once we have suspicion, then send the patient for FNAC, right? So
Yes.
sensitive test plus specific test. So for every cancer we do see cells under the microscope, right? And then that's 100% specific test. So
That is right. Yeah, that is the histological exam. You do that.
Asif?
Yes.
So I wanted to actually repeat again what Suresh asked. So like in the case of diagnosis, it's fine that we would have a sensitivity test where even if we miss out, the specificity test would actually confirm it. But in
No,
terms
no, no,
of
other way around. Other way around. In the sensitivity test, sensitive test you do early on. and you're trigger happy. Like Sukhpal said, na, even a little bit of calcification or something in the mammogram, you declare the person to have cancer.
Okay.
But then as the patient progresses through the experts, you do subsequent and those tests are a bit more expensive. Like for example, you extract cells as Sukhpal is saying and look at it under the microscope.
Yeah.
Those are very high specificity because you can look at the cell and see whether there is cancer or not. Right? So subsequently, the subsequent test should focus on specificity. Why? Because you know that the false positive is not there anymore,
Yeah.
isn't
Yeah.
it? Because you have the confidence that the prior tests were very trigger happy.
Mhm.
That is the point.
Yeah, so my question was like in terms of earthquake, we can't afford to have a false positive case. So how does it work in terms of those scenario? Like,
It's it's a very good question that you asked, and I must say that it is a tough problem. Here, if it becomes like crying wolf. Japan has a system. If they have a reasonably high confidence that an earthquake is coming,
Mhm.
they will they will raise the alarm, right?
Okay.
But it does have false positives, right? So their specificity is not one, it misses out. The trouble with earthquake is you just get one shot. You can't do a barrage of tests, just one shot. No? You either tell people that there is an earthquake coming, and the amount of time that you have to warn is quite literally in seconds, like 90 seconds or 1 minute or something. No? And then it comes, or 30 seconds sometimes. Then it comes, right? That is just enough time for people to run out of the house or stand in the doorway or something like that, or under the table. Trouble is, if you are trigger happy with this test and you keep on sending this alarms, people, it is like crying wolf.
Yeah.
After a little while, nobody listens to the boy because he cries wolf every day. Yeah. So nobody will get out of the house. So that is the danger with all of these warning systems, that you don't want the population to just ignore it. But at the same time, the other extreme is there. You want to have a little bit of a false positive rate, because what you don't want to have is a false negative rate.
Negative.
Right? If an earthquake is coming and you signal
They don't.
something is happening
Mhm.
and you don't raise the alarm, the consequences are fairly devastating. Right? And let me make it very real. It's an earthquake is one, but a much more successful situation is that of tsunami. So when the great tsunamis hit, right, the big tsunami in Indonesia and so forth, and then people ask this question that how is it that we didn't detect? It turns out that the oceans had detectors. They saw, but those detectors were few, and the warnings when they came. See, a tsunami takes hours to reach across the sea and hit you.
Mhm.
People were warned, apparently. They were told that this is coming, but the governments ignored it. In hindsight, why would they ignoring it? Partly because tsunami is such a rare event, nobody really knows what to make out of it. The other situation possibly could have been that people are used to. They say that yeah, this system keeps warning us of tsunami. So now one of the things people have done is they have created a much more robust network of sensors throughout the sea. And when tsunami now comes, we have a very specific test for it. You can see, measure the height of the waves and everything, and you can see the speed at which the tsunami is moving, and you can very precisely tell when it will do a landfall on your shores, when it will hit your shores. So you know precisely how much time window you have to evacuate. See, suppose the time window is very little, you have to make big sacrifices. You ask people to run to the nearest hill, isn't it? And some will be saved and some will drown. But if you have enough time, let's say that you have a day or you have 6 hours or 8 hours, you can mobilize your response system to take the entire population away from the shores, isn't it? You can take them miles and miles away from the shore. So that is the difference between, that is how these things affect actually. It's quite a sea change in how, well, literally is the sea, but quite a sea change in how we do tsunami responses and detection nowadays. So, all right, guys, we have been talking about precision and recall. See, these concepts take a little while to sink in, By the way, if you think that we talk about accuracy, error rate, precision, recall, specificity, sensitivity, that should be enough. No, different literatures talk about different kinds of errors. There is a type 1 error. Type 1 error is the opposite of this thing. It is 1 minus specificity. Then there is a type 2 error. Type 2 error. Now, what is type 2 error? It is 1 minus recall, or 1 minus, you can call it sensitivity. Or recall. So why all of these names all derive from a simple confusion matrix? Why do we have that? The reason is this terminology existed in different statistical and machine learning literatures, and different communities, they used different words for it, and they looked at the situation differently. Modern day, in the medical literature, you talk about sensitivity, specificity, and then in the rest of the machine learning literature, people don't talk about type 1, type 2 anymore. I mean, sometimes they do, maybe, I don't know. But most of the textbooks will talk in terms of precision and recall. Yeah. So recall is the same thing as sensitivity, and precision is different, but people tend to focus more on precision rather than specificity. So that is where we are, guys. That's a set of all the metrics. And remember, all of it is derived from the confusion matrix. All of it derived from the confusion matrix. Confusion matrix. This is an important statement. So what are the things we learned? We learned about confusion matrix. We learned about true positive, false positive, true negative, false negative. We learned about all of these different measures: accuracy, error rate, specificity, right? Sensitivity, precision, recall, type 1 error, type 2 error, and you can cook up some more words. So that's that. And now, we also learned about the receiver operator characteristic curve, the ROC curve, which is the curve of false positive and true positive plotted against each other. Right? And so because it's a trade-off at some point, and the best way to think of the trade-off is to look at this line. Suppose it's one-dimensional data, and there is a region of overlap between the negative points and the positive blue points. Where do you draw the decision boundary? Based on where you draw, you will have your false positive rate will get affected. So that is that. And this is all there is to classification metrics. All of these, guys, will become much more real when we do the labs. What I want to do is in the coming Saturday's section, I want to do in the labs, we're a little bit behind. We are still finishing regression of practical cases. I would like to finish that completely next time. And I would like to do in the next week when we meet, actually, okay, in the next Saturday after that when we meet, we will do classification labs. Right? All of these labs have already released to you in the notes that you have, tabular data, has all these labs. Now, one of the things that I'm not doing is looking at your solutions. At some point, if you should start showing me the solutions. You're working through the labs. Show me the notebooks, because if you're not doing the notebooks, or if you're far behind, it may be worth it. You reach out to me or to the TAs, and we'll help you catch up. It's important to catch up on that. Right? So let's take a 15-minute break, and after that, I will start. We'll go into the practicals actually for classifier. Let's do that for some time. Just a few practical examples for classifiers to make all of these concepts real. It's 8:25 now. Should we meet at 8:40?
Yeah.
Okay. Let's meet at 8:40. I'll just pause the recording for now.
Go with the theory, Asif. Yeah, for now.
Yeah, we can do theory and lab on Saturday.
Okay. So in that case, let me talk about where do these algorithms that you learned fall under the large landscape of classifiers? See, I would say that most problems of predictive analysis in the world in machine learning are classification problems. They're dominant. For example, let me give you a sense of it. You are looking at a picture. This is a very real situation at this moment. We have a test since we are so COVID is so much in our minds these days. COVID-19, so 19. Then people have been wondering how can we have rapid testing. Testing is hard to come by. We do this PT, what is it? RT-PCR, a polymerase chain reaction thing. You take a swab, then you do it. At one time, it used to be a mechanical process. It would take a lot of time for somebody, a human, to look at it and run it and then come back with it. And it would take a few hours. Nowadays, I'm told that we can do it in about 10, 15 minutes. What is the state of the art, guys? The doctors here, Sukhpal and Patrick. What is the state of the art? How soon can the PCR result come back these days? Are you?
24 hours, sir. You can do it a couple of hours.
In a couple of hours, it comes back. Right? And are there enough testing kits now? Like, is the shortage addressed? Has it gone away? Testing kit shortage.
That's depends on the county, sir. But everyone's trying to do their own way to get access to the reagents. It's usually the reagents, sir. But yeah.
I heard at one time that in Fremont, people were lining up from very early morning, 6:30 or so, because the city used to get only about 700 tests a day. And very soon they would run out of it. So people started lining up from 6:30 in the morning. I don't know if it is still true or if it is happening, but there is a thing that this testing could be somewhat in short supply. So people have asked this question: is there an alternative means by which we can test for COVID? The PCR is the gold standard, but either you have it, in which life is great, but if you don't have it, is there a fallback? So in that category, people looked at machine learning. In machine learning, in AI, there is what they did is they took the X-ray of people's chest. Now, X-ray these days is pretty quick. You can have a digital information of an X-ray literally immediately. And X-ray, of course, doesn't take much time. All you have to do is wear some lead cloth and protective cloth and stand before the machine, and then it gets done. Let's say it takes about 5 minutes or 3-4 minutes to get it done. So you can process a lot of people through the system, and those images become available immediately. Can we look at the images and tell whether a person does or does not have COVID, and how accurate is the result? This then around December or early January, there were companies in Taiwan and South Korea, etc., claiming that they have a fairly accurate system. They can detect COVID with a high 90s accuracy, and so they can put a large population through it. It sort of got debated quite a bit because the data that they got was, first of all, we don't have enough data. And 90s accuracy is not good enough. You need to be very, very accurate. Remember the recall aspect of it. The recall has to be very high. So even now, the total data sets available to train the machine learning algorithm is insufficient. But it raises the question, therefore, that is it enough accuracy that we go ahead with it? Right? Some people, and it's highly debated at this moment. Some people say, no, PCR is the gold standard. We should stick to that. We should just somehow make it much more available than it is. But given the fact that we have a limited supply of that test, there is a company, there are a couple of companies that have started marketing this AI-driven test. And what is that test? It's a classifier. You stand before an X-ray machine and X-ray images come. That is the input data. That is your X vector. Goes into a machine learning algorithm. In particular, the algorithm that it goes through is a neural network. In fact, the name of the neural network is COVID-net. There is an excellent paper. Updated version was posted in arXiv on April 15th, just 5 days ago, which talks about this in great detail. It's the guys who have had most success with it. And I believe they're open sourcing everything, making it available. So perhaps it's premature at this stage, but perhaps in the next course, in ML200, we will use that. We will go through a lab exercise in which we use the COVIDNet to predict or to detect COVID in patients, corona in patients. So it is there, and there are companies who are beginning to market it, and there are people who are beginning to deploy it. It is not obviously as good as the gold standard of PCR, but it is something through which you can put a lot of human beings through. India is taking it very seriously, actually, because in India, obviously having PCR kits available down to remote regions is it will be a bit of a stretch. I don't know how successful it will be. So people are very seriously looking at this X-ray based, AI-based solution. And should this become widely used, I would imagine that this would be the first very widely deployed AI-based diagnostic that is at the grassroots level, down to the villages or something. They are making quite a bit of ambitious plans to do that. There's a lot of talk. There is also a lot of debate whether we should focus on it at all or not, but it gives you a sense of what, a practical use of a classifier. Right? Then object recognition, you walk in front of a building, right? Can the camera immediately detect it is you, know that it is you, right? So you don't need a security badge. If with great precision, and it can determine that this is you, then the door can open on its own, right? You don't have to unlock the door with a pass key or something like that, or you can do retina scans and so forth. These are all examples of classification, right? Whether to give you a bank loan or not, whether to, there's so many examples you can think of in classification, which is why a preponderance of effort has gone into classifier algorithms, huge amount of effort. And the number of algorithms that there are ginormous. Like, for example, we did logistic regression. Logistic regression, master it, guys. It is by far the simplest and most widely used. Its limitation is that it looks for linear decision boundaries, hyperplanes as a decision boundary. In real life, decision boundaries need not be hyperplanes. They can be fairly convoluted. They can be like, not regular shape, not planes, and so forth. And so that's where the weakness of simple models like logistic regression begins to show through. You can extend logistic regression by adding polynomial terms, the same trick we did for linear regression. It does work. You can, in other words, with clever tricks, you can extend the usefulness of logistic regression quite far, adding interaction terms, adding polynomial terms, all the things that we learned. And people do that. The advantage of using logistic regression is you get very interpretable models. Things are clear. You see the coefficients in the model, the beta naught, beta 1, and so forth, and you realize how much is the importance of each of the factors. It gives you some sense of that. So that's the value of logistic regression. Likewise, for linear discriminant analysis and quadratic, they're sort of simpler models. But in this literature of machine learning, there are loads of other classifiers we have. And quite a few of them we'll cover in the next workshop, but I'll give you a taste of them. Some of them are actually simpler than even logistic regression or LDA. You ask, how can that be? So one easy way is that you use the so-called baseline rule or 0R rule. You just look at which is the dominant class in the target variable in the data set. Are most animals cows or ducks? Let's say that there are a lot more ducks than there are cows. So one simple classifier can be that you mark everything as duck, because you're likely to be right more than 50% of the time, let's say, if you're doing between cows and ducks, right? So that's sort of a thing, that is called a baseline classifier. Its value is that, it's not value, is not to use it as such, but it sets a benchmark. It sends a bottom line that anything useful must beat this, must outperform this. So your logistic regression, your LDA, it must outdo this. Then another classifier that is quite often used, especially for spam detection, whether your the emails that you receive, are they spam or not? So one of the very, very successful and rather simple classifier that was effective is called the naive bayes classifier. The word naive is sort of misleading. There's nothing naive about the classifier, but it is still a simple model. It uses a basic Bayes rule to determine. Bayes rule is something we'll learn about in the math class. Conditional probability rules to tell, given all the words present, is it spam or not? So it's a classification problem, spam versus ham. Right? You use that. Then there are three very powerful um, areas of machine learning which provide really powerful classifiers. One of them is ensemble methods. In other words, the wisdom of crowds. What you do is you take a lot of learners. You don't create just one classifier. You train a large number of classifiers on different samples of the data and different perspectives on the data. And then you ask these classifiers to vote. Is it a cow or duck? And whichever, if the majority of them says it's a cow, you say it's a cow. When you do it like that, you're doing something called bagging. Then sometimes what you do is you train a model, let's say a decision tree. You train a decision tree. Decision tree is another class we learn about. Then it says that this is the way you'll classify. It will have a certain error rate. Now the second tree you create one more tree, which tries to learn from the mistakes, the errors, and minimize it. So now your result is the combination of the decision from tree 1 and the decision from tree 2. Well, that will still lead to some errors. Now you train one more tree and you keep on going. The idea being that, the first tree may be strong in some areas and weak in another. So the second tree you train for the areas where the first tree was weak and it does well, and so on and so forth. So this process is called boosting. You boost the efficacy by growing more trees or growing more classifiers, but to learn from the mistakes of the previous ones. So this whole family of things are very, very often used in the industry. In fact, if you go to Kaggle and you look at the competition winners, for the longest time, almost all the winning prizes went to people using this ensemble method. So you would see things like random forest, which is like a lot of classifiers and bagging that we talked about, random forest or extremely randomized trees, or gradient boosting, cat boost, XG boost. If you look at the internet and if you look at Kaggle, Kaggle, by the way, is the site where a lot of data sets are published and people publish their own analysis of the data sets. And they run some competitions who can do the best prediction and so forth. So I invite you to become familiar with Kaggle. So you go there, you see how often these ensemble methods win. The second approach that people took is based on a completely different idea. It is called the kernel methods. There is something, a mathematical term called the kernel, but I'll give you the intuition of this. So suppose your decision boundary is not straight, it is curved. One of the insights in math is that any curved surface, or just take 2 dimensions, any curve in a plane, in a page, can be actually straightened out by going to a different space in a higher dimension. It may not even be higher dimension, but just to a different space, you transform the input variables, and a certain transformation will take you to another plane where the decision boundary now becomes straight. Once it becomes straight, then of course solving it is easy. For example, your logistic regression will work or anything will work. So you need methods, you need powerful techniques to somehow straighten the decision boundaries in the underlying data, right? The very powerful methods is the kernel method. The kernel trick is based on the kernel method. What it does is it finds the right higher dimension space in which the data simplifies itself. It becomes so simple that it's now a linear problem and you can go solve it. One of the simplest kernel methods is called support vector machines. Support vector machines were heavily used in the industry for many, many years. Even now it's heavily used. In medical sciences, it is heavily used. Right now, that particular algorithm has quite an interesting history, and I'll probably talk about that history now for a few minutes. It was, so let me, this is how I heard the story from somebody. I think it was from Patrick Winston of MIT, the professor. In his lecture, I think I heard it. So he says, and he knows it because he knows, obviously, the person who created these machines firsthand, the inventor of these things, of these ideas. So there was a Russian, imagine that there's a Russian mathematician who, through Russian winters are very harsh. So you typically go off to your dacha during winter break, and you have your samovars, whatever, pots of tea. You go for small walks, come back, and then you take tea and you think quietly. So he used to live away during those retreats. He started developing a set of ideas. In fact, this kernel method, the idea of the kernel and support vector machines, he pretty much worked out over a lonely winter, alone, sitting alone and developing the ideas quietly over a winter, day after day after day. He worked those ideas out, and it's a pretty remarkable chain of ideas. And it's remarkable that one man could just sit and think through the whole chain. And ML200 will go through the process. It's a very insightful process. So he created this, then he came back, and then he tried to publish it work in a mathematical journal. Interestingly, all the math journals rejected his work, academic journals. They said, this is nonsense. This is not even math. Right? God knows what it is. And it cannot be published. It looks nonsensical. So he was deeply disappointed. And then he tried to publish it in a neuroscience journal, neurology or neuroscience journal, thinking that maybe the mathematical standards there are a bit low. But to his great disappointment, the paper was rejected even there. So apparently for many, many years, he kept sitting on those ideas, and he discovered these ideas in the early 60s. So he sat on those ideas for many years, disappointed that nobody is taking it seriously or willing to publish it. Then in the 90s in US, I believe some companies, was it AT&T Bell Labs or Google or something, I don't know which one, most likely AT&T or something. They were running a competition. I think it was handwriting recognition itself, or digit recognitions or something, but I forget which one. And you were supposed to classify, recognize what is there. And it was an open competition, and the news reached Russia. And those were the days, remember, after Glasnost, after the USSR had fallen, and it was the wall had fallen, the Berlin Wall, and there was much more free exchange of information like today across the world. So he and his friend were sitting there having a cup of tea, I suppose, and then he encountered this announcement. His friend brought it to his notice, and he encountered this announcement, and he said, "You know, you bet I can do better than any of the other guys in this competition using my method." So his friend said that, "Yeah, if you believe so, why don't you do it? You know, this is not an academic journal. They can't reject you. It is just a question of if your accuracy, if your model is the best, well, you win." There was some sort of a prize to that. And so he did that. He actually applied his ideas to that. And when it was received in the US, right away people knew that his ideas had essentially blown it out of the park. Like it was He was playing in a field of his own. Absolutely wonderful ideas. And it led to what is called the kernel revolution in machine learning. A very intense amount of intellectual activity and research and methods and so forth. He obviously today is a professor at MIT. He's quite old now. As you can imagine, in 1960s were the prime days, of course. I think he's still alive, but he's quite old, Vapnik. So his name is Vladimir Vapnik. And Vapnik is obviously considered one of the great legends of machine learning. But obviously, people who are not in machine learning have never heard of him. I can imagine that most of you probably have not heard of it. Any one of you taking the class for the first time, have you heard of Vladimir Vapnik before? You probably haven't. So now you'll realize after some time when you learn about that it is this support vectors, the name of this particular training place, this AI lab, is in honor of, well, literally the support vector machines algorithms and the kernel methods. It's sort of in honor of Vladimir Vapnik. And he was not the only one. It turns out that while he was doing it, other people independently were beginning to come to similar ideas in the 90s. But he seems to have discovered those ideas many, many years before anybody else. And so it was the time, there was a time the ideas had to wait 20, 30 years. And then gradually other people were beginning to come to those ideas. And it is a very active area of research, it was. So that is, from that comes some of the most powerful classifiers, the support vector classifiers. Then there is a third generation of technology. So one is this generation of ensemble methods, bagging and boosting, random forest, gradient boosting, etc. It's still going full steam these days. Many, many problem sets are solved by ensemble methods. Many, many problems are solved by support vector machines. And then there is a third sort of a stream of ideas that came. It has to do with neural networks. Neural networks has had a very, very interesting history. It turns out that the neural network ideas almost go way back to 50s and 60s, right, and 70s and so forth. And a lot of the thinking about neural networks was in place. The core ideas of neural nets were there. Neural nets are something which is simplest way to put it is, we did logistic classifier. So if you can create a fabric of these classifiers, layers and layers of these logistic classifier units, you can lay them together, then it becomes something called a neural net. And this logistic units, you call it the perceptrons, or the nodes in the network. So you create a network of these nodes and neurons. And so logistic is your one neuron. And then you get something like a neural network. The idea is that it was trying to imitate the functionality of the human brain. So the ideas were quite ambitious. It turns out that the human brain is so complicated and so mysterious. We still don't have much clue. We're beginning to get some little bits of understanding of the brain here and there. We understand a lot more today than we understood before. But we are still nowhere close to having a really good understanding of how the human brain thinks. In fact, nobody knows how the brain thinks at all. Right? How it reasons, how it thinks, what is consciousness, what is awareness. There is no understanding, scientific understanding of that at all. As of today, maybe things may change in 50, 100 years, but that's for the future generations. But people started to think that, can we imitate the human brain? They thought human brain is actually modeled after simple ideas. So the neural networks was one idea. It got hyped and it didn't quite work out to its promise. So it went through a hibernation to a winter. Actually, a couple of winters. What would happen is it would get hyped up. Then people would try it. It would not be practically very useful. Then people would ignore it for a long time. And in between, the support vector revolutions came, and the ensemble methods came, and then it was very. But gradually, a group of people, of them, Jeffrey Hinton, who's in Canada, being one of them, they just persisted at these ideas. They kept on working on it, didn't give up. And so, already by 1998 or 99, they had created a network, one of them, Lee Kuhn and so forth, they have created a network called the LeeNet, which was giving you very high accuracy for handwriting recognition or digit recognition. Now, why is that relevant? See, when you send an email, not an email, postal mail, on the envelope you write an address. Now, for a human being to read the address and then sort the mail is very, very inefficient and expensive. One of the reasons the postal system is so efficient is because for more than now almost 20 years, I suppose, they have been using a neural network called the LeeNet, a very successful neural network, which looks at your handwritten address and immediately recognizes it and converts it into a digital address, text. And at the bottom of if you receive any mail, if you look carefully at the bottom, you'll see in the address area, you will see some vertical lines. It is a computer code for exactly the address is now there in the computer code. And what happens is the letter, when you drop it in your mailbox and the postman takes it, that's the last human touch. It goes through sorting machines. They already use the neural network. They automatically code your thing. Then automatic sorters and machine sorters with high volume sorters will redirect that mail into transport vehicles and planes or whatever it is across the country. Let's say a letter goes from here to New York or wherever. It will go to that, and then finally the next human touch will actually be the postman who is actually putting the letter in your recipient's mailbox. Till then, there is no other human touch usually. So the thing has become very efficient. And this is a classic utilization of a classifier because it looks at the handwriting and each of those characters it is able to classify. It's very simple. It is between 0 to 9 and A to Z. It is able to detect what it is, right? About the 36 or 40 odd characters. It is able to detect, classify into those classes. And so it can read, essentially, you can say in quotes, it can read. Very efficient. That's why mail, for the longest time now, is running so very efficient in this country. Now, that's an example of a classifier, and that's a success of the neural net. Then the neural net, while it was already being very successful, people were not taking it very seriously. They said that, incrementally people have squeezed the most juice out of it, and maybe there is nothing more to be done. And for whatever reason, it wasn't because of the two neural net winters. People were not very keen on giving it another chance. They felt that it tends to get overhyped and never delivers. That was a general feeling. I remember that I also used to feel in the early 2000s that, and I was misinformed, of course, but that neural nets are not, they don't quite work as promised. So then in 2006, there was quite a big breakthrough called deep learning, deep neural nets. One of the problems with neural nets is that you couldn't put too many layers together. And there are all sorts of technical reasons why you couldn't do it. And essentially, a lot of the pieces were missing to develop a full effective theory of neural networks. You needed a lot more ideas, and they were being very, very slowly discovered. 2006 was sort of a milestone year when Geoffrey Hinton came out with the concept of deep neural networks by successfully layering many, many layers of the neurons together. And the accuracy that came out of that was astounding, quite high. And so for complex situations where like handwriting, image classification, etc., it just blew everything out of the water. It became a sort of a niche for neural nets. If you're talking about images and videos and so on and so forth, they're extremely effective, far more effective than any other algorithms. Yeah, go ahead.
So you were talking about handwriting recognition, right? So they don't really recognize, they don't really use the address on your envelope, but they recognize your handwriting. Is that what you said? And they mark.
Yes, yes. So when you write your handwriting, you put an address. The first thing the machine does is a neural net translates it into like actual text, optical character recognition. It recognizes what is written, the address, and it becomes now in a digital form. And the digital form is actually there in every letter that you receive. If you look carefully somewhere, you'll see those little edgings or markings. And for the rest of the journey, computers are just reading those markings. The sorters and the routers are just reading those markers, and they're automatically moving the traffic around. That's how it goes. So, so anyway, this breakthrough that came started a third wave of machine learning called the deep learning. People have used the word deep neural nets, and then somebody come up with the buzzword deep learning, right? So deep learning is now the in thing. In certain domains, is very effective. Some people get carried away and say, we don't need any other form of machine learning at all. All we need is deep learning. That's not quite true. There are many areas in which it doesn't do so well, yeah. Or it is like harder to make it work well. There are many areas where data is sparse, or many other situations it doesn't do so well. Other techniques do better. But it is certainly very, very effective in some of the toughest and thorniest problems we were sitting with for a long time. Image classification and image segmentation, for example. So that is, those are all classification problems. A car is looking into the street. Can it see? Can it identify all the objects for what it is? Can you segment it and say, this is a person, this is a tree, this is the road, this is a so on and so forth, pedestrian, a bicycle, a car. Because if you can correctly identify, if you can classify every object in your vision space into the right category, into the right class, then you can decide what action to take, right? So for example, if you're sure that what you're looking at is an empty road, you will drive forward. On the other hand, if you see that there's a pedestrian, you will want to slow down and stop, things like that. So these are all classification engines, very high-speed classification engines in real time. And those of you who have driven Tesla car can attest to it. On highway, it seems to flourish. It doesn't quite work on the city streets, but in highways, people report that the autopilot is quite effective. It sort of works, though you have to watch out. It makes mistakes. But in general, you see all these videos of people on the highway who have gone off to sleep on the driver's seat, right, for a long time, and the autopilot is taking them to work. And for the long journey, they're just sleeping or something like that. Very dangerous thing to do. But the fact of the matter is, people are beginning to trust these machine learning algorithms to such an extent that they are just going off to sleep. So obviously, we are not quite there yet. Hopefully, in a few years, we will be there. But it just speaks to the power of this AI algorithms. And most of these they heavily are classification algorithms. There are other things also happening there, but they're also classification algorithms. So classifiers, therefore, have a rich literature, very rich literature, very high utilization. Another is text processing. In the text world, the way classification shows up is quite interesting. In many innumerable instances, I give you a text. Can you tell which language it is? Classify it into the right language. A very basic thing. Can you do a sentiment analysis? Tell, is it positive sentiment, negative sentiment, and so forth? And today, one of the themes in US is, after all this Me Too movement and so forth, is diversity and inclusiveness, and especially in the context of gender, right? So for example, sometimes when you write things, it has a pronounced male tone to it, and it sort of puts off or discourages women. And sometimes a writing may have a pronounced female tone to it. Right? So the tonality actually is very subtle. And it's not very, humans are not very good at catching the tonality of it. Very good writers and readers can detect it. But the rest of it, we are able to detect it, but not so obviously. It turns out that these classifiers, machine learning classifiers, are very good. They'll tell you that this has a pronounced male tone or female tone and so forth. And you guys, some of you are using Grammarly. And you notice that Grammarly does that. In fact, it is, what is Grammarly? Between a spell checker, which just fixes the spelling of your word, and Grammarly, the gap is that Grammarly is AI driven, it's machine learning driven. So it is looking out for these things. It is looking, if you get the paid version, It is looking out for the tone of your sentences, the construction, the complexity, and so forth, and classifying it into the right thing, identifying, detecting. So that is that. And this classification or detection is very vital. For example, a threat detection. There was one case which is talked about, I believe, in the Freakonomics book. I'll sort of end with that. Apparently, Britain got some signal intelligence that said that there's going to be a terrorist attack in London in the next 6 months. Now, people said, what are the details? And there were no details. All had happened is they had listened to some cell phone chatter, apparently. And this is how I remember it, some cell phone chatter. And they knew that with high degree of confidence, there were some sleeper cells who were already there in London, terrorist cells, and they would become active at a certain amount of time. And then they would do some pretty terrible thing. So the whole question is, how do you find them? If you go to the police, the basic operation would be no body, no case, or things like that. You know, they need very hard evidence and very hard clues to go chase. You can't do police operation without very concrete thing. They will ask who is the suspect. Well, you say I don't know. The whole point is you don't know. Anybody could be. Obviously, the terrorists are trying very hard to blend in. Then you go to the secret services, your spy agencies, and they would also say, give us some idea on who to spy on. Right? It's too hard if you just say we don't know at all. And so this became a case of machine learning, actually, that could you shift through the data and find that sleeper cell network there? And it was a hard problem. And so they started doing that. It was a machine learning exercise. They shifted through a massive amount of data. And they could actually identify, classify people between potential terrorists and not, right? And they did spot those guys. They caught the sleeper cells, the cell, and the disaster was averted. So obviously, they haven't revealed too much about what the machine learning algorithm found. They have revealed only one thing, which in hindsight looks obvious. They found that none of the would-be terrorists had life insurance. Now, can you guess why would they not have life insurance? Anybody?
Suicide bomber.
Yeah, if you're a suicide bomber, no insurance will give a money payout to you, to your family for that. So it is useless to buy life insurance, right? And so it was an interesting and subtle signal that the system discovered. The other signals we don't know about. But when you look at this signal in hindsight, it looks so obvious, isn't it? That it should have been looked at. But the thing is, when you don't know anything, there are so many potential things that you can think of. And also there are so many things that you can't think of, which is, right? And that's the value of machine learning. It can find the needle in the haystack, in a giant haystack these days. We live in a global economy, global world. The threat vectors come from all over the world, right? When they try to intrude into your secure systems and things like that. So almost all security systems today are machine learning and AI driven, a lot of use of classifiers and so forth. So just giving you a broad picture of classifiers. And with that, I'll end the theory part of the classifiers. Next time we'll do, in Saturday, we'll do the labs, continue with the labs. And next week, we'll do change topics and we'll talk about unsupervised learning, pattern recognition, in particular, clustering. We'll talk about methods to find clusters in data and what clusters are, we'll talk about next time. So that is all I have, guys. I'll open this up now for QA, any questions that you have. So please feel free to ask. Anybody? So just to recap, guys, what did we learn through this last 3 lectures? I'll just go from the very beginning. We learned about what classification is. We learned about linear and quadratic discriminant analysis. We learned about the concept of decision boundaries. We learned that there are mistakes. So you can create a confusion matrix. And out of the confusion matrix, you can establish quite a few sort of metrics. Accuracy is one, error rate is another. Then precision and recall are there. then there are concepts like true positive, false positive, true negative, false negative. And it's something that you should get familiar with. And then generally what happens is that there are other metrics which are, you need to sort of develop familiarity with it, precision, recall, and sensitivity, specificity, type 1, type 2 errors. People keep talking about things like that. We did a derivation of the logistic regression here, but then the sigmoid functions and so forth. So we talked about this measures, like what is precision, what is recall, right? So, and we took the example of a medical situation. In the beginning, early tests should be trigger happy. They should have high recall, means they should catch all the positive cases, even at the risk of having false positives. They should catch all the true positives, high recall. But subsequent tests, which just before you give somebody a chemotherapy or something like that, you want to be much more sure that the person genuinely has cancer, because those are fairly brutal treatments, invasive treatments. So then you need more, you want to focus more on precision, or rather specificity, things like that. Then we talked about the true positive rate versus false positive rate, which is called the ROC curve, receiver operator characteristic curve. Give you a bit of a history on where it came from. Then we looked at the area under the ROC curve, which can go from typically half to 1. If your model is embarrassingly bad, it can even be less than half. So theoretically, it goes from 0 to 1, but in practice, it goes from half to 1. And numbers that are like 90, 95% are considered fairly good. I mean, the area under the ROC curve, because the total area that is achievable is 1. So your area will be some fraction of that, between half and 1. So whenever you write your classifiers, do establish your area under ROC curve. These are all the definitions of different metrics. By the way, guys, what will happen is you won't be able to remember this in the first go. It's very, in the beginning, it feels very confusing. So look at page 148 of your textbook, 148, 149. And generally go back and look at it a few times across different days. And gradually it will sink in. You won't remember this definition of all of them exactly. Even I get confused, frankly. If I have not been doing it for some time, then I'll get confused. I would vaguely remember, but occasionally I'll make mistakes. Right? So then I look at the strict definition and get it. I intuitively know what is recall, what is precision, sensitivity, etc. And specificity. Intuition remains clear, but occasionally in the formula, I'll stumble. Right? They all definitions are related across just those four values. So it is all derived from the confusion matrix. So we talked about it. Then we talked about all sorts of classifiers that are there, which we haven't studied, the whole landscape of classifiers. And we talked about broadly the impact of classifiers on real life. Where are they used? What do they do? And that, folks, ends classifiers. So again, let's have a Q&A and then close. Any questions, guys? Was it useful, by the way? Did you guys find today's session useful?
Yes. Yes, Asif.
So I'll put these recordings online.
Yeah, so Asif, so for the COVID imaging test, Alibaba actually released a state-of-the-art model.
Isn't it the same as the COVID net? I thought it's now an open source software.
Oh, yeah, I think it is open source, but I didn't read about COVID net, but they also released it like
Okay.
they released it, I think, in February, that model.
Oh, that's nice.
Yeah.
That is nice. We may be talking of the same model, or we may be talking about different models or different efforts. But yes, it is. So tell me a little bit more about the Alibaba efforts.
So if you go to the chat, I posted the link, so we can look at it.
Excellent. So let me look at that. Let me do that. And the chat. And in the chat, you have machine learning screenplay. Oh, Oh goodness, there's an answer to the question. If the test shows no presence of disease. So in the chat that you guys have mentioned, is there something that I need to write? Because I wasn't reading the chats. Patrick, oh, you have sent it to everyone. Patrick, is it for me to respond to, or is it some information?
No, sir. No, sir. I just summarized the sensitivity specificity.
Oh, excellent. Thank you. And guys, yeah, share over Slack and all of this. Share your understanding of it and see. So let me share what Anil has posted, and let me stop sharing this screen and share another screen that will give us. Application.
As if who's the country now for doing AI research?
What's that? Which
country's number one now in doing AI research?
Almost surely China. They have a.
It is China right now.
Yeah. They are at
India
least
is catching up, but right now it is China.
Yeah, is anyone catching up? Because yeah, I saw like they just made AI a major for like 180 universities there.
Right.
We don't even have. We're just starting at the master's level, but we don't even have that much. So I don't know to China in the future.
Yeah. See, what has happened is China was probably the first. They made They made AI a national security issue. They said that the survival of the country and its future depends on AI. It was perhaps, to my knowledge, the first country that came out of the gate and as a government made it a national imperative to lead in AI. Right? They said that otherwise we'll get crushed. And so the US has also, I think, now made it a national priority. Other countries are also waking up and doing that. But AI or machine learning is no more one more topic you will learn in computer science. It is the central focus of all the countries now, all the strategic, it's a strategic sort of an imperative in most countries. China is, people say, has approximately a 6-year lead over everybody else. One example was that once Microsoft did a demo of, so I think recently they did some demo in which somebody was giving a keynote and that keynote was automatically getting translated into Japanese or something. Pretty impressive demo. And an avatar or a hologram was giving the same speech in Japanese pretty fluently. So it just showed the advance in machine learning for natural language processing, translations, and so forth. And the thing with doing that to give real-time lecture, whatever you're saying, somebody saying it in Japanese or some other language, it is not the text that you transcribe. It is the tonality, the rhythm, the emphasis, and the way you speak. Can you capture the personality of a given person, characteristic of a given person, and translate it into the other language, not just the words? Word is easy. And now it is a pretty impressive demo that Microsoft made. So then what happened is, you all know Andrew Ng, isn't it? Professor Andrew Ng at Stanford, the co-founder of right. So and his original machine learning course, it is almost like a kindergarten. Almost everybody takes that course at some point or the other. You guys can all take that course. It's a free course. So then he sent a pretty provocative email. He used to work at that time in which company did he work with? I think Alibaba or something. Baidu. He used to work in Baidu, right? So he sent a provocative email to Microsoft. He says, "Congratulations, you guys have finally done what we did 6 years ago." Right? And then he gave a reference to the papers that these guys had published 6 years ago on the same work with that result. So it just shows that in some sense, people have not quite woken up to the fact that the center of innovation may not be the US anymore, which is scary at all, actually, from the national security perspective. You do want to feel that this country is at the lead of research, or we are at least comfortable with that idea. But now that idea may not be true. It's becoming more widespread. I think it's a more of what Friedman used to say, a flat earth. The innovation leadership is spreading out to the whole world. The research, for example, the COVID research, etc., you see, innovations are pouring in from all around the world, And Asia is obviously a rising giant, not just China, but all of Asia is a rising giant in machine learning and AI. They're taking it very, very seriously. A lot of countries are taking it as a national, as a survival level priority. Well, it's sort of good news. Good news in the sense that a lot of opportunities exist now in machine learning. I can't think of any startup that claimed to be genuinely doing machine learning and that has failed in recent times. They all get bought up. They all have successful exits. If you remember in the dot-com days, or normally for startups, what is it? 1 in 20 is the success rate. But I don't know what the latest statistics is, but when just by word of mouth, anecdotally, every single AI or machine learning startup that I know about, they all come back and tell stories of successful exit. So the opportunities are huge. It's very fertile. In fact, some very silly ideas and very literally what would be worth a homework exercise, I suppose, in this workshop, sometimes gets marketed and gets acquired as a startup. So opportunities are huge, but with it also comes the fact that with so much of the world intelligence now focused on AI, every the tremendous amount of mind share or intellectual horsepower that is now diverted to machine learning. So what it means is that the progress is happening very, very rapidly. Things are moving quite fast now. And so it is a little hard to keep up. So there is a website, most of you know about archive.org, isn't it? So you know what archive is?
Asif, we can't see your screen.
Oh, you can't. You can't see this? Oh, yes.
It's like very partially available.
Yeah, we can see an edge of it, not the whole thing.
Hello guys, I'm sorry. My WebEx crashed. It just has come back again. So
Okay.
Okay, so we are still recording. Let me share the content that I was sharing. Browser. This.
Okay.
So there is this website, guys. Become good friends with it. Like know it as well as you know the inside of your favorite car. This website, because all the latest research shows up here every day. So pick your areas of interest. For example, if you do AI.
We're still just seeing part of the screen and it's very small.
Oh, you're again having that problem with the screen. Okay, let me change display settings once again, guys. Oh yeah, this is still at 4K. Let me bring down the resolution. Keep changes. Is it any better now?
We can't see anything as of
Not
now.
yet.
Share content and share screen 1. What about now? Are you able to
That's
see?
better.
Yes.
Okay, you're able to. This is excellent. Let me remove this thing here. Now, this website, archive.org, if you're not familiar with it, guys, become familiar with it. This is what I have been engaging with for close to 30 years, right? As I have in the research. I've been trying to catch up research and so forth. So what happens is it started actually with high energy physics or particle physics. As you know, I have background in particle physics. I'm a theoretical physicist. After IIT, I went and did theoretical physics and then also did computer science, master's in computer science. But when I was doing this doctoral work, all the research papers, every morning we used to get it as email. And this organization used to send. It used to be called the Los Alamos National Laboratory. Yeah, it was hosted by Los Alamos National Laboratory, the same place that made the atomic bombs. Right? Well, that is a bit of history there. So now it is being hosted by Cornell University. So all papers show up here. So if you have a paper of interest, you in your field, you just go into your field. You see it here. So you have artificial intelligence, for example, here. You can, and machine learning, you can go into both of these. Those are both areas. Let's see, go to machine learning. Right. you can see all sorts of papers that this is just for today. Do you realize that this papers, archive, they are all just for today that they're coming up. Tuesday, you see, Monday, 20th, Tuesday, 21st, if you go to only Monday, because it's already Tuesday, some places in the world, but here it's still Monday. This is the number of papers. 82 papers were submitted yesterday, right? So obviously this can become rather crazy, and there's so many fields. Just in CS, for example, now machine learning and AI are related. So some people publish here, some there. If you go back up, you can go now to this AI, and there is NLP and so on and so forth, a practical guide to studying. You can see that there's so many papers being published every day. This is the place where researchers publish their work before it makes it to the journal. By the time it makes it to the journal, everybody and his brother knows about that work. Right? If it is a good work, everybody knows about it. But generally, it starts here. So you want to know, obviously you can't be reading all the papers all the time. So sometimes they come up with, and I'll tell you how to go about it. Do you notice that they also have summaries? Archive announces a new COVID-19 summary. Also, see COVID-19 from ArchiveX, medical. Now the people have created dedicated versions of it, medical archive, bioarchive, and so forth. So you can go to just COVID-19 search. And this is the, do you see how much work has been done here? First principles machine learning modeling of COVID-19, beyond just flattening the curve, optimal control of epidemics. And you can read control systems. So much paper, so much research is happening continuously as a stream. So one of the things that happens is, well, how do I know which one to read? Because reading a research paper is arduous. It takes a whole day, right, typically to read a paper. It's not like reading a novel or something like that. So like, for example, if you were to go to this paper, let's see, the latest one there, you notice that it is this background data introduction. So method in data, models of epidemics. So this is the SIR model, by the way, and SIR and death model. These are all epidemiological models. So, you know, when you see those curves and the flattening of the curves, those curves come from these models. Right. So this is it. Somebody trying to do it, creating a loss function, looking at the results. Actually, this paper is pretty short and easy to read. So still, it will take you a couple of hours to read it if you have the background. Actually, this one is very easy. Yeah. Assuming you know the epidemiological model, the SIR model, yeah, susceptible and so on and so forth. So then it is pretty straightforward. You understand what a loss function is. This is. Do you notice that this looks like your sum squared error, guys? Lambda 1 I, whatever it is, we'll figure out what i's are. Infected cases confirmed. This looks like your loss function to minimize. Can you guys get some intuition into it from what we have learned? Does it look sort of like a sum squared loss function? Anybody, guys? Does it look familiar? No one is speaking. Guys, anybody remembers a regression loss function? Least square, you know, sum squared error, least square.
Sum squared error.
Yeah. So this, you notice that it looks very similar to that, and is not exactly that, it's similar to that. It's a sum squared error loss function. And so this is it. And then the rest of it is, how do you guess the parameter? This is then it gets into more of the trading of the neural nets, so forth. And it shows that these guys seem to achieve pretty good results in 5,000 or 2,000 iterations. The log of loss is pretty low, it stabilizes. So I suppose what they will show, they're looking at the UK data. Let's see what the summary says at the end of it. Conclusion, Germany, for different countries they show. France, and all these countries. So obviously country by country, now they're reproducing the results for each of them. At the end of it, let's see what it says. And conclusion, it's always one of the good ideas is start reading by reading the conclusion. Oh, And then it gives references. Okay, interesting. So it's sort of like a letter, just a very quick summary of what is done. So read the abstract of a paper, just read the abstract. Abstract says the corona disease has changed the world, blah, blah, blah. As often said by politicians, the objective is to flatten the curve, etc., etc. Central to the official advice are mathematical models which provide estimate. The accuracy of the model is improved day by day, influence, etc. So it seems like a fairly basic paper, actually. It's a good paper. Method, a data-driven training with both data and first principles is proposed. So there is new research here, right? Results. The output of the analysis are the estimates of infected, etc., etc. Discussion. The methods can be applied to more detailed epidemiological model. So, you get some paper, you see what people are doing, you learn. Some of these papers are very readable, like this paper. Then some papers may not be so readable. For example, let's try this. Oh, this is even more straightforward. Actual chest X-ray. So they are looking at chest X-ray. Is the thing that we were talking about just now. COVID detection, and all of them will give you the GitHub code. The nice thing these days with research and AI is they all give you the code. Researchers are very sharing people. Like for example, this COVID net that I was talking about, CoVNet. Here it is. It's a link to that. Right? And so you can artificial intelligence distinguishing CoVNet, community acquired pneumonia or chest X-rays, so forth. Yeah. So what does it take for you to start using this code? Nothing. The code is there. You can just start running right away. And it's really a pleasure to just take another researcher's state-of-the-art work and read the paper. And in 10, 15 minutes after that, you take the GitHub code and you're running it already. It's really a pleasure to be able to do that. I invite you to do this. Go have fun with it. So this is it. But I wanted to show you something that you may find more interesting or less intimidating. Like you may say, how do I give time to it? So there are people who create curated lists. One of them is called Archive Sanity Preserver. It's an interesting name. What it does is it looks through the archive, and from there it picks up some of the top recent papers in the space of AI. So and now it is looking at last week or last year. You can choose, and it will tell you that in the last year, what are some of the big ideas or big papers that came through. How would you know that there were big papers? Let us look at this efficient mode, rethinking model scaling for complex. If we drill down into it, and the nice thing is they give you pictures of the pages. When you go here, you can see the citations that this paper has received. Where are the citations? Typically, it shows cited as or as references and citations. So if you go here, you will see different this way, citations. This paper has already received 124 citations. This is not some blogs pointing to it. 124 other research papers are already referring to this research paper. So, well, that gives you an idea that this is a pretty serious, references, papers that cite, yeah. This paper, there's so many references to this. Yeah? So obviously it is something important. It is certainly worth your Saturday or Sunday, one day of effort to go and read this paper. So you can click on this. It will take you here. You're looking at this paper now. You can read through this paper. It depends upon level of maturity. I think at this moment, you guys are too early to read these papers. But believe me, one day you'll be able to read all of this. These are not very deep. You just need to, not deep. There's obviously very original work and profound work. But understanding it, you don't need to be a rocket scientist. Once you have learned enough machine learning, all of these things begin to look understandable, though you're still impressed by the originality of the work, of course. So this is one way that I would suggest do that. This is Archive Sanity. Go and pick. Then you can go to the recommended, okay, so it recommended top hype You can see for the last month what are the interface. By the way, this was an interesting work. Somebody tried to create a relationship between algebra and statistics. It's very good. He took ideas from quantum mechanics. I read this paper, so I'm mentioning it. It's a big thesis. He took the ideas in quantum mechanics and quantum field theory. People have done a lot of work creating algebraic theories of it. So this person did a PhD thesis connecting algebra and statistics. No, but through writing statistics is sort of roughly speaking like an algebra. Lovely work, but rather theoretical, may not be of interest to you. This is now literally about COVID, right? Neural network for identifying drug, blah, 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 for COVID and so forth. So that is that, guys. And that's how you go and find the research papers for all this. All right, guys, and with that, I'll end. Anything else? Any other questions? I'll end the recording now.
So, Asif, is it going to take more time long time to clarify the difference between likelihood odds and?
Yes, yes. Okay, let me not finish the recording then. Let me go and answer your question. Good question. Share content. Let me go back to the writing board. Are you guys seeing my writing board again?
Yes.
Okay. So let me bring up another topic here, which is that another topic. This topic is, the question is, what's the difference between probability, odds, likelihood. Are we together? Now, I'll give you a practical way of looking at it. The probability, you understand, the probability of something happening is between 0 and 1, right? You toss a coin, the probability of heads. If it is a fair coin, it's half. Otherwise, it could be based on the bias in the coin. Or what's the probability of getting a 3 on a dice, standard dice that you throw? It will be probably 1/6 unless there's bias in the dice and so forth. So probability of a given event X, outcome X, right? Odds is defined as the probability of it happening and not happening, happening over not happening. Happening over not happening. Or people sometimes also call it success over failure. So what are the odds that Trump will get reelected? That sort of thing. It is the ratio of the probability that he'll get reelected over the probability that he'll not get reelected. So it is probability X over 1 minus Px. Are we together? So this is the definition of odds. Now, what is the definition of likelihood? Likelihood generally means that, suppose I give you a combination of events, something like usually you say likelihood given certain assumptions, right? The likelihood of a hypothesis or something like that. Let me just take an example. Suppose you have a jar. It has green balls, certain green balls, and it has certain red balls. Oh, sorry, red balls. You don't know how many green balls and how many red balls are there. So all you know is you took out 3 balls and they were all red. Now, suppose I tell you that there are 100 balls here. Let us say that the number of green balls or red balls, you pick one, let's say green ball. Proportion of green balls, so the probability that randomly if you pick one, you will get a green ball, probability is Px. X is the chance that you get a green ball whenever you take a marble out of this, a ball out of this jar. Now comes this question. Suppose you all you know is 3 balls came out. Let's make 3 hypotheses. they can, sorry, what just happened? Suppose you have a hypothesis like H1. Actually, let me take it to be, okay, H1, H2. Let me just take two hypotheses just to illustrate the point. Hypothesis one says that 90% of the balls are green, right? And the other hypothesis says 90% of the balls are red, right? So if you think about the first hypothesis says that the probability that you get one green or one red ball and another red ball and third red ball is essentially probability of a, probability of a, well, I said green, right? Actually, let me make it X. X is red. Probability of a red ball. Probability of red, Q. Because you got a red, red, red. And now, if you substitute the value that you believe in the first hypothesis that 90% green means 10%, 1 by 10 is the probability of red, cube. This is your likelihood. Given the hypothesis, given a value of 1/10, what is the probability of getting your three balls all red? That is a likelihood. On the other hand, it will be, by this hypothesis, it will be 1 by 10 cube. By this hypothesis, the probability of red is 9 over 10. So here it will be 9/10 cube, right? So which looks more likely? The second hypothesis looks more likely, right? It is 81 times 3, 81 times 9, right? It is very, very likely, much more likely than the green hypothesis, right? So that is likelihood. Likelihood, you always say, is the probability of a event given a certain hypothesis or certain value for that. So that is likelihood. Does that make it clear?
Yeah, it does.
That is likelihood. So the way it comes up in logistic regression, actually, I didn't go through this derivation in the loss function, is that suppose you have a certain, at a given point in the feature space, the probability that it is whatever it is, it's a blueberry, is there. Now what happens is that xi, probability that this is, so there are, let us say that the blueberries are there. So what you do, what is the joint probability that there will be, the x1 will be a blueberry, x2, let's say that there are three things. X2 is a blueberry, and let us say that you found out that the third data point was actually a red berry. So you have to now multiply it by 1 minus probability of x3. Why? Because 1 minus x3 is the probability that it is a red berry. And so suppose you found blue, blue, red in your data point, and these data points are all different data points in the feature space. So this is the likelihood of seeing the data. So people say that given a probability, what is the likelihood of an actual outcome being those three red balls, or in this particular case, two blues being here, one red being there. What is the likelihood of this evidence showing up? So people often complete the sentence by saying likelihood of evidence given hypothesis. And I would always say that likelihood is a short form of the complete sentence, which is this. Right? So in the case of classifiers, this is the likelihood. So now likelihood is this, but then what do you want to do? You want to build that model, that probability function, which maximizes the likelihood, right? So you want to find that px function that maximizes the likelihood. You say, well, that is simple. I want to pick the hypothesis or that probability function or that hypothesis. which is most likely to produce the evidence that I'm looking at, the data, the training data that I have. Yeah. And so you create a likelihood function, and now you want to maximize this. So max likelihood, right? You need to find a function, but that is it's a little bit hard to deal with products. So one of the things is max likelihood is the same as max log likelihood. If you take the log of it, it becomes more manageable. So then it will become, you notice that it is log px1 plus log px2 plus, and so forth, right? Then log 1 minus px3, like that. And now you say that you have to maximize this. Well, maximizing this is the same as minimizing the negative of this. So minimize log likelihood is equal to minus of all this, all of these things. Now we have a minimization problem. And the moment we have a minimization problem, this is essentially the loss function for our classifiers. So loss function for classifiers is minus log summation over all the positive cases. I is positive cases. Let's say log probability xi, and then minus log negative cases. Let's say not blueberry over ln. Now 1 minus pxj. So when you do this, this is your loss function, though people write it in a slightly interesting way. They often multiply it by the target variable itself. This is what it really amounts to, but people will also put yi right here. Yeah. They will write this typically like this. Why? Because if it is 1, this, if it is 0, then this comes into effect. By putting yi, you basically say that which side is being optimized. So this is a little mathsy and a little hard to digest in the very first go. So we'll speak about it a lot in the engineering math class. But this helps us get a loss function for classification, just as we had a loss function for regression. Regression, it was a sum squared error. For classification, it is this. It's often called the cross entropy loss. There's a very good word for it. Cross entropy loss. Entropy loss. Why it is called cross entropy loss is the fact that the entropy is a mathematical term coming from statistical mechanics and information theory. It stands for minus p log p. Given a probability or a proportion or whatever it is, it's a thermodynamics term. So entropy is a measure of a disorder in a system. So you want to have a loss function that sort of minimizes, that gets you the most order, a discovery of the order in your data. It's called the cross entropy loss function. So this is getting a bit mathsy. I won't go here, not in ML100, but we'll cover it in the math of data science properly. Any other questions, guys, before I close? And if you didn't understand this part, guys, you can ignore it. Huh? Haripriya, did you get it?
Yes, thank you.
Stop the recording now.